Module 3, Part 7. Dear students, this video lecture will be continuation of the previous video lecture where we discussed about communication interface. Under communication interface of an embedded system, we studied one of the interface, that is I2C. Today we will continue with the same topic, the other communication interfaces used in the embedded system. So the first one in today's presentation, we discuss about serial peripheral interface or SPI bus. The serial peripheral interface bus or SPI bus is a synchronous bidirectional full duplex 4-wire serial interface bus. So synchronous means it works with reference to a clock signal. Clock signal is a timing signal with reference to which both transmitter and the receiver devices are synchronized. The concept of SPI is introduced by Motorola. SPI is a single master multi-slave system. It is possible to have a system where more than one SPI device can be master, provided that the condition only one master device is active at any given point of time is satisfied. SPI requires 4 signal lines for communication. They are master out slave in MOSI, signal line carrying data from master to slave device. So it is master out slave in, signal line carrying the data from master to slave. It is also known as slave input, slave data in. Slave input SI or slave data in. The second line of the bus is master in slave out MISO, signal line carrying the data from slave to the master device. Okay, so it is called as master in slave out, slave to master data carrying line. It is also known as slave output or slave data output SO or SDO. Then serial clock SCLK or just SCL, signal line carrying the clock signal. So clock signal line is required because it is a synchronous bus. So slave select SS, signal line for slave device select. Since there can be multiple slaves here, to select one slave at a time, the master requires slave select line SS. So it is active low signal. So the signal is active or the line is active when the signal is low. So it is active low signal. So in this slide we can see the communication using serial peripheral interface bus SPI bus between master and multiple slaves. So there is one master and there are multiple slaves. So this is a master microcontroller or processor. Then we have slave 1 which is EEPROM, slave 2 which is LCD device. So the bus has 3 lines: MISO, master in slave output, then SCL serial clock, MOSI, master out slave input. Okay, and then the slave select line will be present in the master. This is slave select line is not the part of the bus. The pins of master device will have some of its pins as slave select pins. Okay, so depending upon how many slaves it can address or how many slaves can be connected to a master, depending upon that there will be number of pins for slave select in the master. So since there are two devices, slave devices connected here, we can see two slave select pins here. So the slaves are connected via slave select pins, right? We have slave select pin in the microcontroller in the master and also slave select pin in the slaves. So through the slave select pins, master and the slaves are connected. Then other 4 pins are nothing but the pins which are connected to the bus, each line in the bus. So we have 3 pins in the master which are connected to these 3 lines of the bus. Again 3 pins in each of the slave device which are connected to these 3 bus lines. So this is a SPI bus. So now we will see how the data communication takes place in serial peripheral interface, that is SPI bus. Master device is responsible for generating a clock signal. Master device selects the required slave device by asserting the corresponding slave device's slave select signal low. The data outline MISO of all the slave devices when not selected floats at high impedance state. The serial data transmission through SPI bus is fully configurable. SPI devices contain certain set of registers for holding these configurations. The serial peripheral control register holds various configuration parameters like master slave selection for the device, baud rate selection for communication, clock signal control, etc. Now here the baud rate means the rate of data transmission. For example, if the baud rate is 9600, which means 9600 bits are transmitted per second. So the unit is bits per second for the baud rate. The status register holds the status of the various conditions for transmission and reception. SPI works on the principle of shift register. The master and slave devices contain a special shift register for data to transmit or receive. The size of the shift register is device dependent. Normally, it is a multiple of 8. During transmission from the master to slave, the data in the master's shift register is shifted out to the MOSI pin and it enters the shift register of the slave device through MOSI pin of the slave device. At the same time, the shifted out data bit from the slave device's shift register enters the shift register of the master device through MISO pin. Next onboard communication interface we will study here is about Universal Asynchronous Receiver Transmitter, that is also called as UART in short. Universal Asynchronous Receiver Transmitter based data transmission is an asynchronous form of serial data transmission. So here transmitter and receivers are not synchronized. So synchronized protocols require a clock signal generated by the master. Transmitter and receivers work in synchronization with reference to the clock signal, which acts as a reference timing signal. But in case of UART, which is asynchronous transmission or communication interface, there is no clock signal generated by the master because it is asynchronous. Transmitter and receivers are not synchronized. As a result, it requires some additional bit to indicate the receiver that this is a starting of the data and this is a ending of the data, and these bits are called as start and the stop bit, which are appended to the actual data byte by the transmitter to indicate the receiver the beginning and the ending of the each data byte. Now we will see more about the UART. The serial communication settings, that is baud rate, number of bits per byte, parity, number of start bits and stop bit, and flow control for both transmitter and receiver should be set as identical. The start and the stop of communication is indicated through inserting special bits in the data stream. While sending a byte of data by the transmitter, a start bit is added first and a stop bit is added at the end of the bit stream. Now how it is added? The least significant bit of the data byte follows the start bit. The first bit of the transmission will be the start bit, then start bit is followed by the least significant bit of the data byte, then after the data byte the next bit, that is the bit next to the most significant bit of the data byte, will be the stop bit. So first we'll have the start bit, then the 8 bits of data, and then the start bit. Okay, the first bit will be LSB in the data bit byte, and the last bit of the data will be MSB. The start bit informs the receiver that a data byte is about to arrive. The receiver device starts polling its receive line as per the baud rate setting. So the receiver device will continuously, polling means it will continuously check the receive line of it, at the input of the receiver as per the baud rate. That means for every second. If parity is enabled for communication, UART of the transmitting device adds a parity bit. Now this parity bit is an additional bit again which is added for error checking. So what happens is, this parity bit is used by the receiver to check whether there is any error in the transmission. Now how it works? Now if the data byte has even number of ones, parity bit will be 1. If the data byte has even number of ones, parity bit will be 0. Okay, assume that the data byte has odd number of ones and the parity bit will be 1. So data along with the start and stop bit and the parity bit all together are sent to the receiver. At the receiver, if the parity bit received is if the parity bit received is 1, that is same as the parity bit transmitted at the transmitter, but the number of ones in the data is even, so then there is a mismatch, right? Parity bit 1 indicates that the number of ones in the received data are odd, but the received data, if it has even number of zeros, that indicates the receiver that there is an error in the transmission. So some error has occurred during the transmission. Okay, in this way parity bit is used to indicate the error in the transmission. So if the parity bit received is 0, the received data should have even number of ones. If the number of ones are odd, again it will come to know that there is an error in the transmission. Some of the bits have changed their value. The UART of the receiving device calculates the parity of the bits received and compares it with the received parity bit for the error checking. So what happens here? Once the data is received, the receiving device calculates parity of the bits of the received data, as I told just now, and compares it with the received parity bit. If there is a mismatch, it will come to know that there is an error in the transmission. The UART of the receiving device discards the start, stop and the parity bits, since these are the additional bits which are sent to just indicate the receiver that this is the beginning and this is the end, and this is the bit which is used, the parity bit which is used to indicate whether there is an error in the transmission. So these bits have to be removed at the receiver. So UART receiving device discards start, stop and parity bit from the received bit stream and converts the received serial bit data into a word. So this is the connection between two UART devices. Each device will have one transmit and one receive pin. So transmitting or transmitting the transmitter pin of one device is connected to the receiver pin of the other. Receiver pin of the first device is connected to the transmission pin of the second. In this way the data communication takes place serially using UART. So once the 8 bits are received serially, it is converted into a word by discarding start bit, stop bit and the parity bit by the receiver. Next we have one wire interface. A asynchronous half duplex communication protocol developed by Maxim Dallas semiconductors. So this one wire interface, which is one of the onboard communication interface, is developed by Maxim Dallas semiconductor. It is also known as Dallas one wire protocol. It makes use of only a single signal line called DQ for communication and follows the master-slave communication protocol. The one-wire interface supports a, a single master and one or more slave devices on the bus. So this supports a single master and one or more slave devices on the bus. The one wire is capable of carrying power to the slave device apart from carrying the signal. So this is one special thing about one wire interface. So it also, not only the data, it also carries power signal from master to slave. Slave devices incorporate internal capacitor to generate power to operate the device from the one wire. So the slave devices will have internal capacitor which will act as a battery to charge the power which is sent by the master will act as a charging current which charges the capacitor and stores it for usage. Early, sorry, every one-wire device contains a globally unique 64-bit identification number stored within it. Every one-wire device will contain a globally unique 64-bit identification number. We can call it as its address. This unique identification number can be used for addressing individual devices present in the bus in case there are multiple slave devices connected to the one wire bus. So this 64-bit unique identification number will act as address of these slave devices. Every slave device will have unique address, so it helps the master device to identify the slave device which is currently transmitting the data. The identifier has three parts: an 8-bit family code, 48-bit serial number, and 8-bit cyclic redundancy check (CRC) computed from the first 56 bits. So these are the parts of a 64-bit unique identification number. It will have basically three parts: 8-bit family code, then a 48-bit serial number, and then 8-bit cyclic redundancy check computed from first 56 bits, that is 48 plus 8 bits. So in this way, master and the slave devices are connected through one wire interface. So when it is one wire means master and the slave are connected through a single line or single pin. Okay, so master is always microcontroller or processor. The slave can be a battery monitor IC or a EEPROM memory. So we can see here that the line or the bus line here is called as DQ, right? It is named as DQ. So the port pin, single port pin, is connected to a slave via DQ pin. Okay, all these DQ pins of the slave devices are connected together to a power supply, because not only data, DQ line is also used for transmitting the power to the slave devices, right? So if when the connection is from port pin to the DQ of the slave device, it will be sending the data, and when it is VCC to DQ pins of the slave device, it will be sending the power to the slave devices. The same line is used for data as well as power, right? Data comes from the microcontroller which acts as a master. The supply comes from VCC. Now we will see how the communication takes place in one wire interface. The sequence of operations for communicating with the one-wire slave device. First, the master device sends a reset pulse on the one-wire bus. Slave devices present on the bus respond with the presence pulse using the same one-wire bus. Master device sends a ROM command, that is net address command, followed by the 64-bit address of the device. This addresses the slave devices to which it wants to initiate a communication. Master device sends a read or write function command to read or write the internal memory or register of the slave device. Then the master initiates read data or write data from the device or to the device. So everything happens with the help of a single line. All communication over the one-wire bus is master initiated. The communication over one-wire bus is divided into time slots of 60 microseconds. The reset pulse occupies 8 time slots. For starting a communication, the master asserts the reset pulse by pulling the one-wire bus low for at least 8 time slots. If a slave device is present on the bus and is ready for communication, it should respond to the master with the presence pulse within 60 microseconds of the release of the reset pulse by the master. The slave device responds with the presence pulse by pulling one wire bus low for a minimum of 1 time slot, that is 60 microseconds. For writing a bit value of 1 on the one wire bus, the bus master pulls the bus for 1 to 15 microseconds and then releases the bus for the rest of the time slot. A bit value of 0 is written on the bus by master pulling the bus for a minimum of 1 time slot, that is 60 microseconds, and a maximum of 2 time slots, that is 120 microseconds. To read a bit from the slave device, the master pulls the bus slow for 1 to 15 microseconds. If the slave wants to send a bit value 1 in response to the read request from the slave, it simply releases the bus for the rest of the time slot. If the slave wants to send a bit value 0, it pulls the bus slow for the rest of the time slot. So this is about the communication between master and slave in one wire interface. I would like to acknowledge the PPT by the author Shivu KV, who is the author of the textbook Introduction to Embedded Systems. Thank you.